Alright, so today we're going to talk about a matched pairs test, which is a special type of T-inference. So what makes matched pairs so interesting? Well, it actually comes in two forms, so let me describe the characteristics of both. We can either pair individuals by certain characteristics, randomly select a treatment for the first individual, and then individual B gets assigned the other treatment. What individual B gets depends on what individual A got. So there's a pairing based on twins or husband-wife or something like that. Or the second characteristic is that individual persons or items receive both treatments and the order of the treatments are randomly assigned on a before and after measurements are taken. Okay, so they get one more, that the two measures are dependent on the individual. Okay, so in other words, in the second type, the same person gets both treatments, and either it's a before and after thing, so maybe like a weight loss or diet pill type scenario, or like a taste test where they get to try both sodas to determine which one they like better. And in a true matched pairs test, the order of which soda they try first is randomly picked. It's not always the same soda each time. Alright, so let's first look at some examples of different scenarios and see if they even fit the matched pairs definition, and then we'll eventually get to what one does about the matched pairs test. So, a college wants to see if there's a difference in the time it took last year's class to find a job after graduation and the time it took for the class from 5 years ago to find work after graduation. Researchers take a random sample from both and measure the number of days between graduation and the first day of employment. So is this an example of matched pairs? And the answer is no. There is no pairing of individuals. As a matter of fact, one thing to consider is, would the two groups even be the same size? In a true matched pairs test, the before and after have to be the same size, have to have the same number of sample in both. And there's no dependence on one group to the other, so that's another issue. Okay, number two, in a taste test, a researcher asked people in a random sample to taste a certain brand of spring water and rate it. Okay. Another random sample of people is asked to taste a different brand of water and rate it. The researcher wants to compare these samples. So is this a matched pairs test? And the answer is nope. There still is no pairing of individuals. There's sort of a hint of a before-after thing, but there wasn't really a pairing. You had two different groups that didn't even taste the same water to see if they even liked it at the same level or not. So had it been the same group that tasted the two different waters, that would have been a matched pairs, but because it was two different groups, then it didn't quite count. All right, number three, pharmaceutical company wants to test its new weight loss drug. Before giving the drug to a random sample, a company researcher takes a weight measurement of each person. After a month of using the drug, each person weight is measured again. And is this a matched pairs? And yes, it is. There actually is a dependence between the two different types, so you get a before and after situation. This would be the second type of matched pairs that we talked about in the beginning. Okay. Alright, so let's take a look at an actual example. I guess let's take a look at an example with numbers and see if it even fits in matched pairs, and then we'll talk about what to do about it. A whale-watching company noticed that many customers wanted to know whether it was better to book an excursion in the morning or afternoon. To test this question, the company collected the following data on 15 randomly selected days over the following month. Days were not consecutive, just a hint, or a note about that, sorry. Each day they counted how many whales they saw in the morning and the afternoon. So is this a matched pairs? And the answer is yes. Each day that was picked had sort of a before and after approach. So you had a morning measurement and an afternoon measurement. And so you can actually conduct a matched pairs test. Okay, so now that we have the data, What does one actually do with it? Well, what we're going to do is, because there's a dependence, we're going to subtract one number from the other and make a third set of numbers. So let's do this for real quick. Let's go into our calculator and let's actually type in the morning data in list 1 and the afternoon data into list 2. Alright, just kind of show you what I'm doing here. I went into stat edit and I went to list 1, and I'm just going to enter list 1 as the morning data. So 8, 9, 7, 9, 10. So I'm going to get all those numbers typed in. So go ahead and pause the video and type all of that morning data into list 1. Okay, so once I've got the morning data typed into list 1, then I'm going to do the same thing with the afternoon data in list 2. So just start right back up, and kind of like LSRL data, I'm going to, like X's and Y's, I guess, just make sure everybody's partnered up with the right numbers. So we're going to do something with these partnerships. So let me go ahead and pause the video again and type in all of your numbers, afternoon numbers, into list 2. Okay, so now that I've got the morning data and the afternoon data typed into list 1 and list 2, I'm going to go to list 3 and I'm going to make a new column. Now, as far as matched pairs go, whether we do morning minus afternoon or afternoon minus morning, that part doesn't matter. But we do need to document which direction we subtracted this. So I'm going to do morning minus afternoon. So for me, that would be list 1 minus list 2. So go up, highlight list 3, and then go ahead and type in list 1 minus list 2. And the calculator will auto-populate this list of numbers. Okay, and we'll come back to that in a second. All right. Okay, so from here, we're going to do a I know it's a 2-sample matched pairs test, but we're going to do a 1-sample t-inference on that difference list. Okay, so in the 1-sample t process, we need to check all of our conditions. So we have SRS. Well, it's stated SRS in the problem, that the random selection of days for whale watching. We have to state whether sigma is known or unknown, which will determine whether it's a z-test or a t-test. So if it was known, that would be a z-test. T-test would be unknown. And then we need to have some sort of graph of some kind, and that's kind of up to you as to which method you want to go with. This is a normal probability plot, which is one of the graphs we looked at earlier in the course. I'm going to just kind of put it up there. I'm going to do let me do a box plot also, just kind of throw that in there. But this is off of list 3 that I want to do all of these comparisons on. So list 3, and then let's go zoom 9, and it's kind of questionable on the symmetry there, but in our analysis we're going to go with the word approximately, although it is sort of a stretch on the word approximate. Even when you look at the scatter plot, the normal probability plot, you have lots of repeated values on top of each other, which will influence the data somewhat. But anyways, so even though I've got reservations about this, we're going to go ahead and proceed with our t-inference. So the assumptions are met, and then the question is this sufficient evidence that there's a change? Well, let's kind of think about what would happen if it's really if it doesn't really matter. Okay, so let's kind of think about one way or the other. If morning or afternoon doesn't really make a difference, then I would have expected the average to be 0. Okay, that's what I would have thought it would be. So because we ended up subtracting morning minus afternoon, we have to kind of think about directionality here. Where do we think there's more whale sightings? So if I expect there to be more in the afternoon, maybe after lunch they're more visible, then I would expect the afternoon to be a larger number on general, and so I'd expect to see more negatives than positives. So my alternative is going to be that it's less than 0. And again, that kind of depends on whether we did morning minus afternoon or afternoon minus morning, and where we suspect the direction to be, whether we think the morning should have more, the afternoon should have more, from there. Now we do introduce a new symbol. This is mu of d, which is the mean of differences. So we define that to be mu of d is the true mean difference in the well sightings from morning to afternoon. Okay, and again pointing out that our null hypothesis is that there is no difference. Okay, let me kind of back up. Had we had gone the other direction, had we done afternoon minus morning, then I would expect the afternoon to be larger. So I would have had a larger, more positive numbers in it when I subtracted than negative. So we just would have switched it to be positive, greater than 0 than less than 0. Okay, so from here, we're going to do a one sample t-test based on the statistics from that difference column. So let me go back to the calculator, and let's go calculate the one var stats on list 3. Okay, defaults list 1, so I need to tell it to look at list 3. Okay, and then from here I get the mean is negative 0.4. I get the standard deviation of the sample is 1.639. We had 15 numbers, so putting that all together, I can set up our t-score, which works out to be negative 9.45. And then that p-value is based off the TCDF. So let me again remind you of how we calculate that, because it might have been a while. So to get that 0.18, I want to go to the distributions menu, look for TCDF, and then I want to think about what I'm trying to do here. I suspect it's a lower tail test, that it's less than, so I would do if I want to go from negative infinity up till that lower tail. So negative 1 e to the 10. And then upper would be that negative 0.945. Degrees of freedom, so there's 15 in the sample, so n minus 1 would be 14. And so that's what it should look like when we type it in. And then I hit enter and I get a p-value of 0.18. Now when I compare that to our alpha 0.05, let's kind of make our statement here. Our p-value is actually greater than alpha, so we failed to reject the null. There is insufficient evidence to suggest that more whales are sighted in the afternoon than in the morning. Okay. How could we make this a stronger conclusion? And we failed to reject. The p-value is pretty insignificant, being 0.18. But if we had a larger sample, maybe we'd be able to have a stronger conclusion. So anytime we increase sample size, that sort of it has an impact on how accurate we can make our predictions. Okay.